Hello class, welcome to Big Bang Data Science Solutions Ramadan program, which is over, but we have two more sessions to complete this project. And now we are in week number 9, and we were supposed to complete supervised learning, but we are going to go back to week number 8, and we are going to complete decision tree classifier. So we are going to do decision tree, and we are going to learn the math behind it, or how this decision tree works. As we already mentioned, we talked about this in the previous sessions, that data science is simply a method of trying to mimic the way we human beings make decisions. So we make decisions, we make many decisions every day. We make decisions based on information provided to us. This is called information-based decision making or learning. We learn to make a decision based on comparing two things and trying to find their similarities or dissimilarities. That is called similarity-based learning. Then we make a decision because we have some numbers, we have some facts, we have some probabilities. That is called probability-based learning. And we make a decision because of a past decision that we made, and we learn from it. Either we fail or we were successful, we learn and we improve our decision management, decision making in the future. So these are some ways that we as a human make decisions in our daily lives, especially those big investment decisions, or decision that requires a lot of thinking, a lot of effort, a lot of it's die or live decision. So we in those decisions we really do decision based on either information based, similarity based, probability based, and error based. So we want to build systems that mimic the way we make decisions. Now we want to build systems that learns or help to make decisions based on the information. We want to build systems that make decisions based on the similarity or probability or the error. In terms of information-based decision management or learning, we are going to talk about decision tree. So this is the algorithm we are going to learn today. So we got some data that we are going to use to help us understand the logic behind decision tree. So this is the data that we have. This is called historical data. And we got, of course, this is the data to predict. In the historical data, we got the target variable. And as you see, this is a binary. Then since it's a binary, then we know that we are going to do classification. Okay, and so we decide to do in classification, there are many algorithms, and we decide to do decision tree. Okay, the process of building a decision tree is a process of building a machine learning. So number one, we are going to identify X and Y. Number two, we are going to split. Number three, we are going to import the model library. Number four, We are going to train the model. Actually, we are going to import the library and initiate the model. We are going to train the model. Number 5, we are going to test the model. Number 6, we are going to compare the actuals versus predictions. So these are an overview of the overall steps required to build a machine learning. Okay, and we are going to use decision tree. So what is decision tree? Decision tree, in a nutshell, is simply an upside down tree that uses the rules. So decision tree, what it does is going to treat. So the first thing we got to do with the data, we need to pre-process it. We need to prepare the data. And one way to do this is simply we are going to remove features that wouldn't add any value to our analysis. So we are going to remove the student name, because I really don't care who you are. Don't care about your name, but I care about what your behavior. I care about your characteristics, your specialty, your difference, what makes you different than others. So I care about the age. We are going to keep age. We are going to keep marital status. We are going to keep reading hours, TV hours, sleeping hours, and of course the target variable. So we are going to remove the student name, because this is simply too personal information we don't need, none need. Okay, and of course we got marital status. We need to transform this marital status into numeric, using of course one of the available transformation method. Most likely it is going to be the dummy variable. So yeah, and what do we have? When we're talking about decision tree, it is going to treat, decision tree is going to make decisions on how to split using either entropy, number 2, Gini index, number 3, classification error. It must be number 4. I don't know it, but decision tree is using either entropy. Entropy is how uncertain you are. So the uncertainty or Gini index or classification error, but this in our case we are going to use the entropy. We are going to use the entropy. And the entropy is a mathematical formula which is the minus probability of 0 multiplied by log 2 probability of 0 minus probability of 1 log 2 base to probability of 1. So, and I need your help. So number 1, how many ones and how many zeros that we have in historical data? How many ones and how many zeros?
4 zeros
You got 4 zeros
and 3 ones.
and 3 ones. Okay, so the first step that decision tree is going to do is going to, number one, calculate the overall, number one, overall entropy. So we are going to do here the probability of 0, which is, so what is the probability of 0? So you got 1, 2, 3, 4, 5, 6, 7. So 0, you got 1, 2, 3, and 4 is going to be 4
over 7
over 7 minus 4 over 7 log 2 4 over 7 minus 3 over 7 log base 2 3 over 7. So this is the overall entropy. How uncertain we are. If let's say that if Saliha calls in, if we have Saliha, how sure that we are, let's say that Fatima, Z, and Jeremy, how sure, how confident we are that they will graduate or they will fail, they won't pass. That is called the chaos, or they call the uncertainty. So let's assume, no, I don't have time to do the math. Let's assume this is around 0.8. Let's assume that 0.8. Okay, so the overall formula is 0.8. And now the decision tree is going to treat every single element of your data with an equal weight. In other words, decision tree is going to split our data on age, is going to split the data on marital status, it's going to split the data on reading, okay, it's going to split data on reading, reading hours, TV hours, etc. Okay, how if the feature is numeric, it's going to split and the mean. What is the mean? What would be the mean for 21, 43, 36, 40, 43, 19, 60? Just give me a number. What is the mean?
we're around 40. So, yeah.
38.
Mm-hmm.
This is greater than 38. This is less than 38. Okay, if it's not categorical, we are going to split on the most frequent. What is the most frequent? Okay, S, M, S, D, S, M, S. What is the most frequent?
S.
Is equal S not equal S. And the same applies for all other features. But we are going to take a look into one feature so you can understand the process. So, okay, so we got 11. We got 4 zeros and 3 ones. Okay, out of the 11, how many do we have less than 38? We got 1, 2, and 3. We got 3 here.
Hmm?
And above 38, we got 1, 2,
4.
3, and 4. Good. For these 3, how many zeros do we have and how many ones? We got 1, 0, 1,
2.
1.
2 0.
So we got 2 zeros and we
1 1.
1, 1. And in the other side, how many zeros and how many ones? We got 4.
1 2.
We got 1 0,
2 zeros.
2 zeros. Yeah, we got 2 zeros. And of course,
2 ones.
2 ones. Good. And now we are going to apply the entropy. So let's do, so this is called the left hand side. And this is the right hand side. So let's do the entropy of the left hand side first. So we got 3. So the 0 is going to be 2 minus 2 over 3 log base to 2 over 3, then minus
1 over
1
3.
over 3 log 1 over 3.
1 over 3.
Okay, I believe it's plus the left hand side is going to be minus 2 over 4 log 2 over 4 minus 2 over 4 because this is a 2 log base to 2 over 4. So this is the formula of the entropy. So we calculate the entropy before splitting. This is before and this is after. And we are going to do entropy, and we are going to calculate the entropy, and we are going to calculate the entropy for all features. At this point of time, any questions, any concerns, please?
I'm good. Oh.
Others, please speak up. Any questions, any concerns? Z, SZR, Samshul, Shahid, Saliha, Noreen. Any questions, any concerns, please?
No question so far.
Sounds good. So let's assume, because we don't have math, let's assume this entropy is equal 0.1. This one, for splitting an edge, the entropy of splitting an edge is 0.1. The entropy on splitting on multistatus is 0.3. The entropy on splitting reading hours is 0.5. The entropy on TV hours is 0.47. The entropy on sleeping hours is something. So the way this decision tree works, as I said, it is going to split. It's going to split all our features. is going to make split on all features provided. It's going to split on age. If it's numeric, it's going to split on the mean. If it's categorical, it's going to split on the most frequent. So it's going to split in age. It's going to calculate the entropy before, the overall entropy. This is how uncertain we are. We are 80% uncertain to determine if students will graduate or will fail. And of course, we want to decrease this value here. The better, the smaller the number, the better our accuracy is. Now we are 80% uncertain. I cannot determine 80%. Then we are going to move to 50%, 40%, 30%. 0% uncertain means I'm 100% accurate. I'm 100% confident. So we calculate the entropy. The decision tree calculate the entropy before any split. Then it's going to split on all features. If it's numerical, it's going to split in the mean. If it's categorical, it's going to split on the mode. And it's going to calculate the entropy after the split. So this is step 2. Step 3, it is going to subtract the entropy before. So entropy before minus entropy after. And this is called information gain. Okay, so we are going to find the information gain of each split. So unfortunately, decision tree is going to keep only one split. It's going to keep only one split, and the one split that's going to keep is the one with the highest information gain. Okay, and let's assume for now that the age is the best splitter. So we are going to get rid of this for now. Yeah, let's assume that the age is the best splitter, or the split that yields the most information gain. How do you find information gain? Is subtracting the entropy before split from the entropy after split from the entropy before split. And once we determine the best splitter, then we are going to repeat. We are going to repeat the process. So now what do we have? We got age. And we split on 38. And we got 3 and the left hand side, and we got 4 in the right hand side, and of course we got 2 zeros, and we got 2 ones, and we got 2 zeros, and we got 1 ones. Okay, and now we are going to repeat the process. So we are going to calculate the entropy. Entropy before, and now we are going to split the left hand side using so this is the left hand side. We got 3, we got 3, and of course we got 2 zeros and 1 1. We are going to split on age again. We are going to split on marital status again. We got 3. Marital status. We are going to split on marital status again. We are going to split on reading hours and TV hours, sleeping hours, etc. So we are going to split on 1, 2, 3, 4, 5. 5 features. Then we are going to calculate the entropy after. And we are going to after, then we are going to subtract the entropy of splitting on this left hand side on age, subtracting that from the entropy of the age. Then we are going to calculate the entropy of the splitting the left hand side on marital status, subtract it from the entropy of the age. Then we are going to calculate the entropy of reading hours, left hand side sleeping splitting or reading hours, then calculate the overall entropy, etc. And we are going to keep only the feature with the highest information gain. Let's pretend that the best splitter, the left hand side, the best splitter is marital status. So we are going to split on marital status. So for the marital status, we got, so out of these 3, we got, so this is 1, this is second, and this is the third. And we are going to, so we got divorce, we got single, So we are going to split on a single is equal to single, not equal single. So I need your help. How many out of this left hand side, how many singles do we have? How many singles we have out of these 3?
3.
Singles.
We
3
have
singles.
1, 2, 3.
No, ma'am. You guys
No.
not get it. So we split on, start over. We calculate the entropy for everything.
Yeah.
Then we assume that was 0.8. Pretend that was 0.8. Then we split on age, on marital status, on reading hours, TV hours, sleeping hours, and we find out that age was the best splitter. Okay, so far so
Okay.
good. And for the age, we got 4 above 38 and 3 below 38. And now we got to repeat the process. To repeat the process, now we are going to split on the children of age. So the entropy, we are going to start with the left-hand side. In the left-hand side, we have 3 elements, less than 38. And we find out that splitting on marital status was the best. So now let's split on the marital status. Out of these 3 elements of the left-hand side of the age below 38, how many singles and how many non-singles?
Two singles.
Yeah, we got 2 singles and non-single,
It's 1.
1. For these 2 singles, how many zeros and how many ones?
For 2 singles, 1.
So we got 0,
1.
we got 0, so we got 2 zeros.
No, the other 0 is for non-single, right?
No, we got 2 singles.
This is,
Yes.
yeah, 2 singles, 19 and 36, 1 0 and 1 1.
Okay, you got 1 0 and 1 1.
Mm-hmm.
We got 1, 0, and 1, 1. And how about the below single, not non-single? We got 1, right? And so how many zeros do we have?
1.
1 0.
1, 0. And how many zeros do we have?
Zero's 1, like we don't have any ones for this.
So, and we got a 0 of 1.
1. Yeah.
So for this one, how many classes do we have now? How many classes do we have?
2 classes.
2.
Either 0 or 1. Either
Yeah.
add weight or fit. So when we split on age, 38, we got 2 zeros and 1 1. How many classes do we have?
2.
3.
No. How many classes?
0 or 1. 0 or 1.
We got a 0 and we got a 1. So when you have more than 2 classes, that simply means you need to split down the road.
Okay, gotcha.
Okay, so we split on marital status and we split on marital status equal single or not equal single. For the equal, not equal single, how many classes that we have?
Only 2 classes.
What are they?
These are
0.
1s and 0s.
I'm talking.
Graduate or not graduate.
Yeah, I'm talking. No, brother, just follow me. I'm not talking about this. I'm talking about this one. So we got how many classes, how many elements of the data that we have under 38?
Three.
How many students? 3.
3.
Okay, out of these 3 students, how many are single and how many are not single?
2 single and 1 is not.
Okay, for 2 single, for the 1 is not, how many we have zeros, how many are ones?
1 0. 0 of 1.
Then how many classes that we have for this this left hand side?
1 only.
So we got only 1 class. Okay,
Yes.
that means we stop here. We are done.
Okay.
This one does not require any further splitting.
Splitting it.
For this one,
Got it.
we have 2 classes. We need to split down and around. How do we split again? Can you tell me? How do we split? We are going to calculate the entropy of this one left hand side, right hand side, right? We are going to split on age. We are going to split on marital status again. We are going to split on reading hours,
Reading hours.
on a TV, on all features. And we are going to calculate the entropy of all entropy of this. Then we are going to subtract and we are going to keep only 1 splitter. And this is how decision tree works from the top all the way to the end. So are you guys clear about the process?
Yes,
Mom, I
I'm
have a
good.
question.
Yes, ma'am.
Yes, I understand the process of entropy and the splitting until we get to a single variable, but how is this actually done? Is this through coding? Because I don't think this is going to be done manually.
No, it's coding.
in a-
No, it's coding. It's 1 line of code.
Okay, and it's a pretty standard one. You have to kind of develop that based on what you're dealing with the data that you have.
Yeah. Can you? What is your question again?
Well, the question is, okay, it's coding, but it's a standard code to create this process of entropy, or is something that you have to develop based on the data set that you have,
No,
something that you have to kind of rewrite.
It's a library we are going to use, and we are going to use it today.
Okay, thank you. I'm
But
going
this is
ahead.
the math. This is the math behind the scene.
Yeah, that's very useful to know
Yeah.
how these things work
It's
behind
all
the
math,
scenes.
all statistics and math, but luckily we don't do this. If
Yeah.
I do this
Okay.
manually, I'm gonna give up. This is too much. And imagine you have a million of records, and you have a couple of hundred thousand, couple of hundred of columns. It's gonna
Yeah.
take you 5 years to calculate this.
Yeah, no efficient at all. Yes. Thank you, Mo.
Yeah, this is not. But still, your job as data scientist is at least to understand the concept behind it, how decision tree is working, and this is how decision tree works using entropy. If you were
More one
to,
quick question here before we move on. Can I ask the question now?
yes, ma'am.
So, like, we are splitting based like the trees. Like, how do we know? Like, I understand where to stop the splitting. So, is there anything like if we have like a more trees, more trees, is that a good model or something like that? Is there anything like that
Uh,
based on the number of trees we have?
it is going to be one tree, but if you let it go, the
Mm-hmm.
question probably that you would ask, do we let it go all the way to the end? When do we need to stop? So now we need to keep doing this for the left hand side, then we are going to do the same for the right hand side, then the left
Mm-hmm.
hand side of the right hand side, and we keep going all the way to the end.
Mm-hmm.
If you let it go all the way to the end, you are gonna end up not learning anything. You're simply memorizing the position of your data. You are gonna
Okay.
overfit it.
Okay.
So when do we stop? We stop when we reach a purity. When we have one class per node.
Okay.
We stop when we are gonna tell it, hey, stop after 5 split.
Okay.
We are gonna tell it, hey, you stop. We stop here.
So how do we know that we stop after 5 splits? How do
We
we
tell
know
it. I
that?
mean,
Like while coding.
you have, yeah, in the code you are gonna tell it, hey, after 5, stop.
Okay.
Don't let it run all the way to the end. It is nothing wrong with it, but it is gonna overfit.
Okay.
So we stop it when we reach the purity, means one class per node. We stop it if we have a threshold. We stop it where we don't have any more data. The most accurate way the most accurate method is to stop with a threshold. And this is the decision tree in nutshell, without going into the heavy math behind it. Jeremy, are you clear?
Yes, I'm clear. Thank you.
You're welcome. Okay, so if you guys don't have any question, any concern, I will be more than happy to move into the coding. So I'll give you 1 more minute to see if you have any question, any concern about this. Asad, are you clear? Afifa, Haina, or Hena?
Yes, brother.
Are you
Yes, I'm
good?
clear.
Good. Okay, folks. So this is a pre-processed data. This is not the original data. The raw data has a lot of problems. So we removed some dimensionality using the correlation analysis, using the prior knowledge. Then we did transformation of target categorical into numeric. Then we replaced the question mark with an unknown. We did a lot of work. Okay, and so we got this data. It's been transformed. It's all zeros and ones, which is good. And now we are going to read this data into this file. Okay, so let me clear out the output. Okay, the first thing we gotta do is we are gonna import some libraries, NumPy, Matplotlib, Pandas, and this is what you are gonna learn if you were to take the short program. You are going to learn pandas, numpy, matplotlib, and seaborn. Okay. Then we are going to import. Yeah, we are going to import file number 4. Okay. Our insurance claim number 4. So this is insurance claim number 4. It's preprocessed. The only concern that we have with this data is we got one column, the high values, but really don't care at this point of time because we are using decision tree. It does not really matter. Decision tree handles outliers, handles missing values, handles categorical data efficiently. So you don't really need to do any pre-processing with decision tree. Okay, we are going to read the data, and this is our data, and let's take a look into our target variable for the reported. Yeah, let's take a look into our target variable. We got 75% of the historical claims that we dealt in the past, they were legitimate, and 25% they were fraudulent. This is a very good number. This is a critical number we are going to use later so this is our base. So now we are going to visualize it. So this is our ones and zeros. Okay, the first step is to identify the machine learning algorithm that you are going to use, the X and Y. So what is X? X is all features except the target variable. All features except drop is except the target variable. Y is the target variable. So we need to identify X and Y. Number 2, we need to split the data into 80% and 20%. So we got 1,000 claim. And randomly we are going to split on 20% or an 80%. Yeah, it's really up to you to determine the percentage of splitting, but this is the common. This is not a rule, but it's common among data scientists. It's 80%, 20%. So go with the rule, just keep it 80%, 20%. So in 80%, we are going to have X and Y, and 20% we are going to have X and Y also. So 80% is called training, and 20% is called testing. So we are going to have testing, features, and testing target for 80%, for 20%, and we are going to have training, features, and training target for 80%. So this is X and Y, this is X and Y. Any concerns about this at this point of time?
I'm good now.
Okay.
No.
So we are going to split. So we identified X and Y, we split. And now we already know that this is what we have in the historical data. If we were to guess, we are going to guess based on what we have in the data. Okay, and I gave you this example in the past. If your spouse, you're married and your wife is pregnant, she's been pregnant 5 times in the past. And every time she was pregnant, she delivered a baby girl. So the last 4 times she was pregnant, she delivered a baby girl. And now she's pregnant for the 5th time. If you were to guess, you are going to say she's going to be a baby, a girl, based on what you have in the historical data. Based on what you have in the past, you are going to make a guess. And the guess is simply a guess. It could be right, could be wrong. So if you were to guess a claim, like if someone just called in, and if you were to determine what is what would be the type of this claim? Is it legitimate or fraudulent? We are going to guess at 75%. So we are going to tell the management, okay, so we don't have, if you were to guess, it's going to be 75% legitimate and 25% fraudulent. And it's up to you to do something. So this is our base. This is what we are going to compare any model we are going to build in the future against this value. And we want a model that beats this value. We want a model that does better than guessing. If we have a model that does the same as guessing, then we don't need you. We don't need a model. Why do we need to code and go through this exercise? Simply go ahead and guess, and you are done. But of course, guessing is not what we are trying to. We want to go beyond that. So for the scikit-learn library, it has a class called dummy classifier, which you can apply on the most frequent and the zeros. But we already know, we already have the value is 75%. Let's do that very quick. There we go. And let's calculate the accuracy. It's 75. Okay, if we were to guess, our baseline is 75%. Now we are going to build a decision tree. So we are going to import the classifier. Yeah, we are going to, from the scikit-learn. Scikit-learn is a huge library. Excuse me. It does support this. This is the website. Please Google it, scikit-learn.org, or just go through this website. It does support classification algorithms. In classification, we have linear models, linear and quadratic discriminant analysis, kernel ridge. We got a lot of modelings, and does inspect, visualize, got a lot of other things that this library does beyond machine learning. Okay, it does support regression. In the regression, we got decision tree, not decision tree. Regression. Here we go. We got this is all the models, and if you were to take our 30-week program, we are going to cover most of these. Ordinary square, ridge, lasso, elastic net, then Bayesian regression, logistic regression, then simple linear, multiple linear, support vector machine, kernel ridge, etc. There is a nearest neighbor. The others, a naive-based decision tree, ensemble method. We cover this. We cover all of this. Then it does support clustering, where you don't have a target variable. This one, we have a target variable. For classification, we have a target variable, and the target variable is either binary or trinary or multi-class. Regression, we have a continuous target variable. Clustering, we don't have a target variable. And on the top of machine learning, it does support dimensionality reduction through modeling, model selection, pre-processing, all type of possible techniques that you can use to pre-process our data. This scikit-learn supported. It's a great library. Okay, so we are from this website, we are going to import the decision classifier. Okay, and we are going to initiate the decision tree classifier with minimum parameters. So number one, we are going to tell it, hey, go ahead and use entropy. Go ahead and use entropy. You could tell it, go ahead and use gene index and other methodology, but because we learned the entropy, we are going to use it. So what is this decision tree is going to do? It's going to look into the data, it's going to split on every single feature. It's going to split an incidence severity total loss, then it's going to split on the mean and the insured hobbies crossfit, and the mean is going to split on all and every feature that we have. So we got 33. So it's going to split. We are going to have 33 splits. It's just one split. Then this decision tree is going to calculate the overall entropy, and then it's going to once we split, it's going to calculate the entropy of each split, and then finally it's going to keep one split with. We are going to subtract the entropy after we split from the overall entropy, and we are going to keep the one with the highest information gain. And we keep looping and repeating the process all the way to the end. Okay, and we are going to split and we are going to store that. We are going to store that in a feature. Yeah, and let's remove this for now. Then we are going to store that in a decision tree model. Okay, and so we just initiated a model with a few parameters. So we are going to use this model to train our 80%. Yeah, this is a training feature, and training target is 80%. So we are going to train our model using the function fit on 80%. So all the work that we explained to you guys through Entropy, it took this decision tree 9.08 milliseconds to complete. Very, very fast. Now, I know maybe, was it you, Carolina, who asked the question?
I guess so, yes.
And I know one student, I don't remember who, they was, are we doing this manually? No, it's not. So the model has been done it in 9.08 milliseconds.
Wow.
Decision tree,
Yes.
and we have 1,000 features, 1,000 records, and we got 33 features. If you were to do it manually, it's going to take you 5 months to do it. Okay, so now we trained the model. We learned something, but we don't know how good this something is. So what we got to do is we are going to test it on the 20%. Yeah, we are going to test it on our 20%. So we trained the model on the 80% X and Y. But now for testing the model, we are going to test the model on only X. And we are going to hide the Y. We are going to tell the model, hey, we don't have the Y. Can you help us determine the Y? And the model say, yes, I will do my best based on what I learned from the historical data. The model does not know that we have the Y. We are going to pretend that we don't have it. We are going to hide it from the model, and we are going to see how good the model is going to do in our 20%. That's why we did not include the Y test test underscore target. We did not compare. So this is our X and Y. So we are going to test the model on everything except the target variable. And whatever, so the dot predict function, it is going to make an attempt to create a column similar to the column that we hide, except that the column that we hide is what we have in the data, and the column that's going to be created is a prediction, is an attempt to determine what would be the value. So let's do that, and whatever data that we have generated, we are going to store it in an object called DT pred, decision tree prediction. Okay, and now we are going to compare the actual, which is this target, with the prediction. So this is the prediction. We've got 0, 1, 0, 1, 0, 1, 200 0 1s, and the target variable is 0. So we got the actual was 0, we predicted as 0. So in the first case, we did a good job. The actual was 0, but my prediction was 1. This is very bad. The actual was 1, and my model did 1. This is good. Then we got a 0 and 1. Then we are going to calculate how many times we are off, how many times we mispredicted a value. So to do it manually is a nightmare. It's going to take you a while to figure it out. So what we got to do, we are going to use the same library, scikit-learn, and we are going to use a few metrics: accuracy score, classification report, and confusion matrix. And okay, so we are going to import from this scikit-learn. We are going to import accuracy score, classification report, but we are going to use, there are many measurements we can use, and these measurements are covered in the 30-week program. But for this short training program, we are going to concentrate on confusion matrix. So we don't really care about this. All we need is confusion matrix. And confusion matrix is simply cross table that compares the actuals with the column that we hide. It's called actual target variable, from the column that was generated by the model is called the predict target variable. So we are going to compare the reality to the representation, reality to the prediction. And in the real life, we have, in the actuals, we have either a 0 or 1. And the prediction is going to be either a 0. The prediction is going to be either a 0 or 1. Okay, so we are going to compare the actual to the prediction. If your actual is 0 and your prediction is 0, then very good. If the actual is 0 and the model predicted as 1, this is very bad. We made a mistake. If the actual is 1 and the model said, no, I think it's 0, then it's very bad. And if it's 1 and the model predicted as 1, it's a good prediction. So 0 to 0 is called true 0 or true negative. 0 versus 1 is called false 1 or false positive. 1 to 0 is called false 0 or false negative. 1 to 1 is called true 1 or true positive. And out of this confusion matrix, we can extract a dozen of different calculations, different measurement. F1 score, recall, precision, area under curve, sensitivity, specificity, type 1 error, type 2 error. There are many measurement, some of them they have the same function, the same formula. But out of this confusion matrix, we have a dozen of measurement that we can extract. But the one we are going to use today is called accuracy. And the accuracy is simply the true negative plus the true positive divided by true negative plus true positive plus false negative plus false positive. So this is the formula if you were to get a percentage closer to 1. Okay, and now we are gonna run the confusion matrix to compare the feature or the column that we hide from the model, the actuals, and from the column that the model generated. So here we go. So we got, this is our confusion matrix. Okay, so this is 0, 0, this is 0, 1, this is 1, 0, this is 1, 1. Of course, this is good, this is good, this is good, and this is bad, this is bad. So this is 51 of zeros, and we got 49 of ones. Okay, out of this 151 of zeros, the model made 26 errors. Out of the 49, the model made 17 errors. So the total errors that we have is 13, 2, 3, and 4, 43 errors out of 200. And to calculate the accuracy is going to be 125 plus 32 divided by 125 plus 32 plus 26 plus 17. In other words,
It should be 200.
yes, I know, but just I want to give it in detail
Okay.
and understand
Okay, got it.
where the 200. And if I say 200, I said where is the 200?
Gotcha.
The 200 is the 20%. If you guys, when we split the data on 20%, where is it? 20% of 1,000. So we got 1,000. So you got 1,000 feature. So we split into 20% is 200. So if you ask where this 200 is coming from, that is our 20% of the 1,000 claims that we had in the encircle data. Okay, so this is the accuracy. If you did the math, I would probably say it's around 70, probably 6 or 77. Let's take a look. Okay, and now we are going to do the accuracy. Yes, I deleted. Okay, let's take a look into the accuracy.
3.5.
78.5. I was very close. 78.5%. Can anyone interpret this 78.5 for us, please? Just try. What does it mean, 78.5?
The prediction was 78.5% correct,
What does it mean?
meaning it matched the actuals. The prediction matched the actual.
That is not the right question. If you were to explain, if I'm a layman, I'm your manager or
Okay.
from HR, and I called you, Mr. Assad, your model is 78.5%. What does it mean? I want you to explain to me in a very simple English.
And my predictions are 78.5%.
Yeah, please hold on.
Correct.
To help you, please go back to the what we have in the data. We got 75% and 25%. We got 75% of what? Of zeros, legitimate, and we got 25% of 1. So
The
this is the
fraudulent
base.
claims.
Yeah, this is the base. So we got 75% of legitimate claims, legit claims, and fraud claims. So our base was 75%. Our model, so this is our base, means if we were to guess if someone would have a legitimate claim or fraudulent claim, with the best we can guess is 75% they are going to be legitimate and 25% they are going to be fraudulent. And now
Mm-hmm.
we built a model at 78%. What does it mean? 78.5
The accuracy of the model.
accuracy. Yes.
Accuracy is improved.
So the accuracy here means if, for example, let's say Afifa just calls in to report a claim, if your model says that Afifa is legitimate, she is legit at 78.5%. If the model says Afifa is liar, she is lying, she just committed a fraud, she committed a fraud at 78.5%. And the question is this a good or bad model?
It's a good model because it's more than what we expected, the 75. But is that acceptable in the real world? If I was a manager trying to minimize my claims, my fraudulent claims, I want a 95% accuracy. That's what I want.
So my question is this good or bad?
It's good in comparison to what we have. We have a 75%, and now we have a 75.5,
You think
78.5.
my question, do you think I'm willing to pay you 160,000
No.
to give me two level?
3% more, no.
I'm gonna kill you if that is the case. That is not, it's not a good model.
Yeah, I wouldn't pay that. I mean, I don't know anything about data science, but for a 3% of a claim,
Yeah.
that is going to be more accurate? No.
No. So yeah, it's a good model compared to the base, but it's not a good model. So would have happened? You know, what is the problem? So when you are not happy with the accuracy, there is many directions that you could take, many levels. You could check. You could check the model at the parameters level. We could check the data at the transformation level. We could check the analytic approach. We could check the models themselves. There's many things we can check, and is another nightmare. But right now, let's take a look into the model, into visualize this model. So this decision tree, it comes with one feature, one element is called it's called feature importance. So this decision tree uses all the features we provided to it. Is 33 features. Mathematically speaking, some of these features does not have any value. Do we know them? Yes, we know them. So let's figure them out. So the model used, yeah, these are the percentage. So for example, this is one, auto mod 95, it has zero correlation, zero influence. Some models have 0.10, 0.06. Now let's sort them. Let's visualize them. Here we go. So some features they have higher influence. Some features they have zero influence. Some features they have just okay influence. So for example, vehicle claims has the highest influence to determine if a claim is fraudulent or legitimate, followed by incident severity, by hobbies. hobbies is an important feature to determine if you lie or if you tell the truth or you lie. So what we could do, we could simply take out auto model 95. We could take out the insert hobbies video games because they really don't add any value. They're simply slowing down the process, and we could take them out. Okay, and now, yeah, so these are sorting them out. Vehicle claims comes first, 36%. Influence on the decision of making decision tree decision, followed by insured hobbies, incident severity total loss, insured hobbies crossfit, etc. If we were to take only the 5 first, we could build a model using the 5 first elements or 6 first elements. Now we are going to visualize this decision tree. We are going to use a library called export graphs. Yeah, I'll provide the code later today. Let me uncomment this for now. And let's cross the fingers. And this is a template, just copy paste, and it's going to work. Here we go. So this is our decision tree. So what do you think we did wrong with our decision tree? This is from last two weeks ago. What do you think we did wrong? So what do you think about this decision tree?
Very deep.
That simply means, very deep means very complicated.
It might overfit the data.
And it went all the way to the end of the data.
Mm-hmm.
So that is an indication that this decision tree memorized the position of the data rather than learning patterns from the data. So what do you think we should do?
Lower the number of columns or variables. That would be
Talking
one.
about this is the decision tree. What do you think we should do?
We can ask it to stop after certain levels, like
We have to stop it.
yeah.
So this is one level. This is 2. This is 3. This is 4. This is 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, etc. So we could stop in 1, 2, 3, 4, 5. Please do that. Let's remember, when we let this decision tree drive all the way to the end, the accuracy was very bad. So the model probably did a very good job on to 80%. It could be 100% accurate, but when we test the model on 20%, it did not do well because it was overfitting. So now we are going to stop it. To stop it, we are going to apply max depth. I want you to go up to 4. And you could play around this.
Yeah. More to what extent the actual columns that we pick are relevant in this case, because we can stop the decision model, allowing the model to learn from those variables that we allow. But in the previous, we pick, I believe it was, we remove the name and we have the single file, like the marital status and the age. So maybe there are other 2 things that are more relevant, that it could be age and it could be, I don't know how many.
This is simply an example trying to explain how decision tree works.
Oh, okay.
And for our code, we are using a different data set. We are using an actual data from our insurance.
Okay.
So this was an example. Simply,
And the colors that we're gonna get from the data set of the insurance is gonna be picked by the decision tree model, or is something that we're just gonna feed directly out of all the columns in the insurance data.
I mean, if you were to use this data, for example, the model is going to determine which features to keep and which features not to keep.
Okay, so it's now to us. Okay, got it.
Okay, so now we are going to stop R4, run it again. We are going to stop R4. We are going to train the model again. So this one is 3.99 milliseconds. It's very faster. Now we are going to hide that single feature, the actual from the prediction from the model, and we are going to compare. So remember, we got 17 and 26, and now we got 6 and 25. So we reduced, we did a better job. Now let's calculate the accuracy. Is 84.5. Okay, 84.5. So compare.
I've got a question.
Yes, sir.
Yeah, have we at this point lowered the number of variables where, say some had no effect?
Let's take a look into the
Yeah.
variables again.
I see.
And here we go. So now we got a lot of variables. So the model did not use all variables. Before, if you see before, when we let it go all the way to the end, the model used used every elements of your data. So simply memorize everything. So right now, all this, we don't have a bar, that's simply one excluded. So we got, let's take a look into, sort them out in the descending order. So we got incident chase. Now the incident chase hobbies is the most predictor, followed by vehicle claim, and we got a lot of zeros. So we could build a model using only 1, 2, 3, 4, 5, 6, 7, 8, and 10. 10 features, and we are going to exclude everything. And this is what we are going to do. We are going to override. Yeah, we are going to keep, we are going to remove all the zeros. So now let's override our data. And go. So now we got an override data, and we are going to start from building, sorry, we are going to start from okay, learning a model, fitting the model. Okay, then we are going to test the model, do some prediction and confusion matrix. We got 625. We still have 625. Why do you think it did not change? So
utilizing the same variables.
Why? No, we are not using the same variables. We are using less variables now.
Because it had already figured that those did not affect the.
Yes, sir. Yes, sir. That is the answer I was expecting, because the features that we removed, they have zero. Either you keep them or you use them, still is going to be zero. They don't have any impact. So if you keep them, it's going to slow down the process, because the model has to go through them anyway, regardless if they are going to use them or not. The model is going to use them, but they have a zero. So we removed all the zeros, and now let's take a look into these features. Confusion matrix, accuracy, still 84.5, and Let's see what happened. Or insurance. Sorry guys, I need to split. I need to split the or. I forgot to split. So I'm gonna go back all the way to X and Y, because now we are going to identify X and Y. We are going to split. Okay, and now we are going to build a model again. Then build a model. Take a look into the features. Confusion matrix 625, accuracy 84.5. Now let's take a look into the features. So we got only few features. Visualize them. Here we go. And the highest, the most accuracy, in short is. This is very this is surprising, honestly. You might think that probably the best indicator would be age, marital status, income, but it turns out to be hobbies, and it turns out to be a chase hobbies. What would be the explanation? I have no idea. We need to consult a psychologist to answer this type of question. Okay, take a look, and we got all our features, and now we can build a decision tree again. There we go. Very, very simple decision tree. And we are going to stop here. So as you see, this is our target variable. We started with an entropy 0.8. Then we split on easy incidence severity. Easy greater, less than 0 is true, above the 0, etc. Then we split again, we split, and we got a class. So let's say that Afifa just calls in. She calls in to report a claim. And I'm going to ask you questions, Afifa. If you don't mind, can you please help us? So what is your incidence severity? Is less or higher than 0.5?
I can't really see the screen.
Just say yes or no.
Yes.
So is it less or higher?
Higher.
So it's going to be false. And is your hobbies is your chess? Your hobbies a chess? Yes or no?
No.
So we go in this direction. And is your hobbies CrossFit? Yes or no?
Yes.
Then you are a liar. So that's the way it is. So we go in, depends on
It
you.
might be wrong too, right, Mo?
Yeah, and we have, you are a liar 84.5%. But we could be wrong 20, almost, not 20. It's going to be 16 or 14, 15%. Okay, let's pick another one. Let's Muhammad Khan. Please do yourself. You just called in to report a claim. Question: is your incident severity minor damage greater than 0.5 or less than 0.5? Muhammad Khan. Okay, let's Asad. Do you want to try?
Yeah, sure. Okay, so first of all, this is severity that we are checking, or the percentage of claims with severity higher?
The incident is a minor. Is it a minor? Yes or no?
Oh, this particular one? Okay. Yeah, so it's not minor, it's major.
So it's
Greater than.
It's false. Okay, it's false. So we got this direction, right? Then the,
I thought it would go the other way. I'm saying it is higher. No,
it
the
says here
incidence.
it is less than or equal.
Oh, I see. Okay, got it.
So let's change your mind. Yeah, you say it's less. Okay, we
Yeah.
go in this direction. And is your total loss greater or less than 0.5?
Incidence severity loss. Okay.
Let's say that you say it's less.
Okay, let's say.
Then your vehicle claim, what is the value? Is it less or greater than 14,910?
Greater.
Greater is going to be, I believe, this direction. Is insured hobbies, do you like camping?
Yes.
Then you are a liar.
Okay.
84.5, you are a liar. 25 to 15% or 14%, you are telling the truth. So that's very simple. Simple as is.
Okay.
Any questions, concerns about decision tree?
I'm good, Ma.
Okay, folks, that's it for today. See you guys tomorrow. Tomorrow is going to be our last session. Please make an attempt to join us, and we'll be happy.
Hi, Mo. I have one quick comment.
Sure, ma'am.
I tried to set up an one-on-one appointment for yesterday.
Yes,
I was able to do it to Calendly, but I did not get any confirmation or anything. I don't know why.
there is no calendar for Friday. Yes, there is one for Friday.
Yeah, there was one, but I didn't get any. I logged into the meeting session.
My
I didn't
apologies.
see.
You should have told me. Please next time.
Oh, okay. I thought I know something. You must be busy, so.
No, I mean just call me. Just call me. Just
Oh, okay.
text me
Okay.
through.
Can we do sometimes next week?
Yeah, please go ahead and do it, and just notify me through the WhatsApp. I will be more
Yeah,
than
sure. I will do that. Thank you.
Okay, folks. I'll see you guys tomorrow. Until then, you guys have a great evening, and bye, everybody.
Okay.
Thank you.
Assalamu alaikum warahmatullahi.
Assalamu warahmatullahi ta'ala.
Thank you, Salama.